All right, so today we're going to talk again about steady state flow, and this is a prelude to pseudo-steady state that we'll talk about on Monday. What's going to be the fundamental difference in your mind between steady state and pseudo-steady state? To look at it, what fundamentally is going to be different? Anybody? Will the equations look similar? But there'll be a time component. And what do you think that time component is going to reference? Sorry? What's the time component going to reference? Yes, but the extra term that's going to be on, let's say, the radial flow equation out here, it'll be plus some term. What's a good hieroglyphics thing? The little crow thingy, maybe with a top like that, times time. So what's inside of this term? What's the most critical element inside of that term? What was our last lecture on? The one before that, then. Nice tie. Yellow and blue makes green. Job interview? Probation hearing? Immigration? Come on. Come on, bring it back. Be like Marmina. Say something about, you had to work for it. You're not a lucky sperm cell like me, huh? But you are. Actually, I'm a luckier sperm cell because I was born in Louisiana, but that's okay. Okay. Oh, here we go. First of all, I got a stalker. Now I got a bunch of people hate Louisiana. This is great. So what's inside? It's Jesus, right? You ready? What's inside the big J term? Actually, we shouldn't write it this way because you're going to confuse it with the productivity index. So how can we write this? How do you write J in Egyptian? Yeah. How do you write J in stone? Yeah, it's probably like a flower or something with some petals, that sort of thing. Actually, that looks more like Groucho Marx, but that's okay. All right, we're just going to make Dilhan's favorite symbol, which is a penguin. It's a red one, okay? It's communist. How's that? All right. And it's multiplied by time. So what's inside of our communist penguin? I'm sorry, for the Kazakhs, it's a socialist penguin. Socialist, right? You were never technically communist, right? But when you were a little girl, you were in the Young Pioneers? You're not going to admit it. I had a student one time from Russia, and she told me, she goes, when I was a little girl, I felt so sorry for you stupid Americans. Now I hope you feel sorry for me. I feel sorry for everybody because they're not me. So there, how's that? All right. Jesus, you ready to take this back? All right, so what's inside the communist penguin? Sorry, the little red penguin. Fish. What else? Blood, okay. And I think what he's saying is that there is a compressibility term and an oil in place term, right? Why is that, Mr. Stone? Sorry? Okay, but the thing that's going to control how pressure behaves with time is going to be mass or volume, correct? And the energy component, which we know is compressibility. So the terms that we'll see for pseudo-steady state are going to look very similar to this equation, except they're going to have another term. Now, Stalker Boy, I want you to tell everybody how we're going to derive the pseudo-steady state equation as opposed to how we derive the steady state. If you get that right, I won't pick on you anymore this semester. But since you're going to get it wrong, okay, while we're still young, stop looking at me like Jack Nicholson in The Shining. Come on, man. Anybody want to help out, Marmina? Back row? Middle row? Skid row? Come on. Dilhan, you want to, is he still here? What do you do, sneak out? Oh, there you are. You want to help him? Okay. Did you understand that? DP? Yeah, that's because you weren't listening. So we're going to have a mass continuity equation. What's that known as? Miss Leva? You get. I didn't even see his lips move. Okay, material balance. Let's see if we can do this. And then we need an equation of motion. Marmina, that's not E motion. That's equation of motion, okay? So, anybody want to tell me what that one is? Stop winking at me, boy. I'm telling you. Does your mouthpiece want to answer for you, Miss Leva? Take a wild guess. Think French. Sorry? This is Darcy's law. Okay. It's Darcy's law. I'm writing it on here. Jeez. Are you blind, you fool? Come on. All right. So to derive the pseudo-steady state part, we're going to take the mass continuity equation and the equation of motion, and we're going to marry them in a state that allows it. And what's going to happen then is we're going to solve the resulting differential equation. Now, how do we solve for the steady state relations? It's very simple by comparison. Because there's no time-dependent term, we just integrate Darcy's law. Is that okay? So in this particular approach, the way we're going to derive the equations later on in this lecture is we're going to take the particular form of Darcy's law and we're just going to integrate it. And we're doing the simple ones today. We're going to do liquid. Dilhan has this distorted view of reality that we're going to keep making you do harder and harder questions, but that's fine. That's okay. I think the quiz on Monday, it's going to be tough. We'll give you some insight. We'll actually tell you when we're on the slide that it has something to do with, but it's going to be tough. Just so you know, I want to be fair. How about a hug? Okay, So now that we've established that doing the steady state thing is pretty easy, doing the pseudo-steady state is going to be a pain because we're going to have to derive what's called the diffusivity equation by taking the mass continuity equation and the equation of motion, putting them together, creating an equation, and then it's a second-order partial differential equation. How do you solve second-order partial differential equations? Since he's too far for me to reach, would you thump him in the back of the head? No? Anybody else? How are we going to solve analytically, thank you, a second order partial differential equation? Sorry? Or do you mean separation of variables? What are you eating? Yeah? You might want to move over a little bit. Yeah. It looks human. Louder. What the hell is he talking about? So you're saying separation of variables. How many agree with him? Wrong. Okay. Sorry? And how do you do that? We're not going to use substitution. Y'all are going to make me beat my head against the wall. How do you solve second order partial differential equations? You have to reduce them first to second order ordinary differential equations, right? And how do we do that? There's two methods. Mr. Bueno. No habla English. Where's the Venezuelan? How do we solve second order ordinary differential equations? For this course. For this problem. Yeah, I thought so. Actually, I was saying that we're going to solve the partial. Sorry. Any idea? Can we use the Laplace transform? I need a hug. Okay, she agreed. So we use the Laplace transform. That's whenever we do the transient solution, which is going to be another week or so. And no, you're not going to be expected to do that on the test unless Dilhan writes that problem. Okay, right? Yeah, maybe. We'll throw that in. Okay, so how are we going to take a second order partial differential equation and reduce it to a second order ordinary differential equation? There's a real easy way to do it. We're going to cheat. And we're going to say that the pressure change with respect to time is constant. The pressure change with respect to time is constant. Third time, the pressure change with respect to time is constant. We're going to talk about all this again next week. What did I just say, Marmina? With respect to time is constant. What's that the definition of, Marmina? That is a definition of pseudo-steady state. That the pressure at all points in the reservoir change at the same time. Everybody stand up. Everybody stand up. Stand up, stand up, stand up. Okay? Okay. So let's do the wave. Everybody ready? This side of the room, stand up. You guys kind of go woo like this, okay? Ready? Woo. All right. And then back. Woo. Okay. That's pretty good. Now, are we actually going to have waves in the reservoir? No! Okay, we have distributions. So instead of going sinusoidal, it's just going to kind of propagate out. So slowly, this group, front row, follow me. You're going to kind of go down a little bit. Now you guys follow. You guys follow. You guys follow. Oh, this is great. This is working. Okay, keep going, keep going, keep going. All right, that's the pressure. I had to stand up. I'm old. You don't have to stand up. You can stay down. All right, so now what I'm getting at is don't sit down. What's pseudo-steady state going to look like? Get back up, get back up. That was transient. We just did a transient wave. Well, not really a wave, because you can't say wave. Oh, I bet you wish you could do that, huh? Okay, so, ready? We're going to do pseudo-steady state. So everybody, at the same time, down, same rate. Everybody. So what's happening is that I'm going down, and Guillermo's going down, and Loco's sitting on his ass, pardon me. That's an observation well, okay? It doesn't count. But the rest of us are going down at the same rate. So the pressure in this reservoir is changing at the same rate. Do you think that's going to happen a lot? Y'all can sit down. If you're a reservoir, you think you're going to spend a lot of time in pseudo-steady state? Yes. You're going to spend most of your time in pseudo-steady state. Why? Remember our wave thing? Let's do the wave again. I liked it. Come on, up. Come on. All right. Loco, you're on my list, boy. Everybody ready? Let's do the wave. Slowly, slowly. What controls the speed of the distribution? Y'all keep... All right, excellent. Sit down. Permeability controls the speed. Okay? Not the volume, not the rate, a little bit on the compressibility and the porosity, but 90% of it, or vast majority, will be permeability. Okay? Oh, that was good. All right. So we're not dealing with pseudo-steady state today, but I enjoyed it. So once we have a transient that is propagated all the way out to the boundaries, then all points begin to change at the same rate. That's the definition of pseudo-steady state. What's the definition of steady state? Ready? This is going to be fun. One more time. Marmina, you're making me look bad. Mr. Beard. Everybody ready? Now what I want you to do is the guys in the back, you don't move at all. The guys in the middle, you go down about halfway. The guys in the front, we're going to go down all the way, but we're going to stop. Ready? Follow me. We're going down and stop. That's steady state. Never changes. That's what it's going to be like. So is it real? No. Sorry? I'm trying to show off your mood swing. Oh, by the way, I gave a little speech. How many of you know we had a petroleum engineering student killed in a car wreck this week? It's pretty serious business. And I think we need to take a moment and remember that person. But we also need to remember that 4 a.m. driving down the highway is not a good idea for young people. So I don't want any little crosses by the side of the road for you guys. It's a terrible tragedy. But if you think you're about to do something stupid, that's probably a pretty good sign that it is stupid. So don't do it. I'm not saying that's what happened to him. But I guarantee you, as the oldest person in this room, by probably a factor or two, I've done a lot of stupid things I shouldn't have survived. But, you know, it wasn't my time. Please don't do anything stupid, especially on your Valentine's Day. You know, oh, stop, man. Oh, God. Let me take, yeah, you have no idea why. All right, so today what we're going to do is we're going to talk about linear flow. And in this case, I've drawn this diagram such that if I'm a molecule, I'm going to move from higher pressure to lower pressure, and I'm going to move through this system because there's a lower pressure here. There's a pressure at the well, and there's a pressure at the outer side like that, and we're going to move across. This is exactly what you did in Petty 311. Somebody tell me if it's possible to achieve this in reality other than in the lab. No. Can you make a reservoir simulator do this? It's going to be pretty tough. Why? Why is a reservoir simulator not going to want to produce steady state flow? Nope. I guarantee if I ask Dilhan, he'll give me a $5 answer, and every word of it will be correct. But it boils down to one word. What is that word, Dilhan? Mass accumulation. A simulator operates. It's Turkish, okay? Sorry about that. Is it mass accumulation? Compressibility. That's what allows us to produce. Otherwise, we're going to have to fictitiously inject into this system. It cannot produce like this naturally. It has to produce like this under some sort of induced condition, right? And if there's any compressibility in the system at all, this condition will not be met, right? There will be a time-dependent term. What's the hardest thing for a reservoir simulator to do, Mr. Little? It's like little boys. It cannot sit still. Mathematically, when you're running a reservoir simulator, if nothing's happening, it's going to make something happen. Out there in the round-off, little things are going to start happening. It's unstable. It's a numerical solution. And the same thing's going to be true with steady state. Forcing a reservoir to produce at steady state conditions is going to require you to impose a physically inconsistent condition on that reservoir. Again, I just want to make the point. So now what we're going to do is very simply, as Mr. Zanero was trying to say, separate, right, Mr. Zanero? And integrate. So let's go to the next slide. And don't worry, Ms. Leva, I'll get these slides up today, just for you. I'm back on track. Every time I go off track, oh, and by the way, Ms. Leva wants 5 homework problems next week. So it is written, so it shall be done. Bilhan, I want you to be on me like, you know, I was going to say like a bad toupee, but thank you, you bunch of perverts. Okay. That is our goal next week, is get out all the homeworks that are due before exam 1. When's exam 1? March 6th. To quote Franklin Delano Roosevelt, a day which will live in infamy. Okay? Sorry? Technically, you're right. I'm glad you feel the bond. How's that? Shut up, man. Take your damn Ritalin, will you? All right. So let's go back to Darcy's law. And we're now going to separate and integrate according to the Zanero process. Why did we do it this way, Mr. Zanero? The most important words in the first line is that B mu is equal to a constant. Otherwise, what happens? If they're not constant, they're a function of pressure. And then we got a problem. Okay? So now we've separated, and we're going to simply write our integrals. We can do this. We're going to integrate from 0 to x. We're going to integrate from pw to px, pw, sorry, like that. What's the integral of dx, Mr. Stone? X. Yeah. Okay. What's the integral of dp? Okay. So far, so good. That higher math hasn't stumped you yet. Now, when we solve this, eliminating that, and we solve it for rate, we have QSC, which is standard conditions, the, what do we call it, the units constant, Ka, B mu, Px minus Pw. Dylan made me listen to these tapes this morning, or to these videos. I do a lot of shouting. Did you guys notice that? And I'm sorry about that. It's my personality. Stop looking at me. Man, you're like my chihuahua. You always got one eye on me. You okay? All right, so now we're going to solve this for pressure. Px is equal to Pw plus 1 over Cx. The rate, B mu, Ka, times x. Now, if we plot this, this is PR. This is our pressure profile out here. Here's the slope. And of course, this is as a function of position. What's wrong with doing it this way? What's wrong with, I mean, yes, we're creating building blocks for understanding reservoir behavior, but what's wrong with showing you this plot? Are you ever going to see pressure measured in the reservoir? 3 options. Yes, no, or maybe. This is a flat earth guy. He says no. This is our devout liberal. She says yes. You say maybe. Now explain maybe. How can it happen? She doesn't have to, because she's a believer. You know, It's a belief system, not a scientific basis. He's just a doubter. Okay, so I want you to tell me how maybe this could happen.
How maybe pressure could be measured, or how it could be?
Maybe how we could measure pressure out in the reservoir. Anybody want to help her? Does anybody lay awake at night and have fantasies of how this could be done? Louder. We're not going to have test wells. We're not going to have observation wells. Sorry? That's only measured at the wellbore. But good point. That's why we're having the course. So we're only going to measure things at the wellbore. Thanks for that reality check. It's not an insult. I mean, an insult would be you, okay? So now how do we measure pressure out in the reservoir? Maybe. When you listen to our dean talk, let me see if I can get this down. Science boils down to bio, info, nano, right? Help me out. Nano? You think it's going to be nano? You're going to inject a little probe out in the reservoir and it's going to send messages back? Maybe. See, there's the answer, maybe. Now, how would the Russians do this? I know you're not Russian. She's Russian. We're focusing now on how the Russians would do it, or how they'd say they'd do it.
Would the pressure be...
Okay, your turn. Sorry? Okay, no correlation. This is the whole reason we do reservoir modeling. Because we can't measure it, we model it. How many people like that, okay? Yeah, I know. You make $150,000 a year running reservoir models that nobody knows how to prove wrong. Pretty good deal. Mr. Arthur's like, yeah, I'm going to give me a job like that. He'd like being a tax auditor, huh? Money's better. Okay, so how would you measure the pressure in the reservoir if you had some technology? Could you inject some kind of special fluid in the reservoir, stimulate the reservoir seismically, and get a pressure measurement from that? Can you inject some kind of fluid in the reservoir? It deforms, you produce it back, you get some sort of message from the reservoir. Can you use some sort of a Y connecting grid with resistivity and maybe create some sort of, sorry, I said no correlation, but some sort of inference of pressure from inside the reservoir? Nope. The only way to measure pressure is to measure pressure. But this nano thing caught on, right? But how big are pores? They're ittle bitty, tiny, little, I'm crushing your head, small things, right? Okay. How are you going to get something in there that, I don't know, has a radio in it or, something like that? Anybody? Tyler, that pencil tastes good? Yeah? Okay. Yeah. Did you eat all that meat? No. I just want to know when you keel over dead who's going to give you CPR, because it ain't going to be me. Anybody? Sorry? Okay. But how small are they? Yeah. And they like pristine environments. So when we send this thing down there and it's like really hot and really high pressure and there's some nasty chemicals down there just waiting to say, nano machine tastes good. What about biomachine? Yeah? When they first started doing microbial oil recovery, the stuff they were injecting to feed the microbes to get them started, was like 10 times the price of a barrel of oil. So this is not necessarily something that's going to work. But there are people, a company called Tiorco does do microbial enhanced oil recovery. But I'm not sure, Mr. Arthur, do you think the microbes are going to take a little, note, kind of like Mr. Plankton and SpongeBob, write down where he's been and what he's doing? I mean, any of this stuff is possible. Saudi Aramco says that they're going to use materials like this, right? They're the only ones bold enough to say it. They have. Have you guys seen the presentation? That they're going to use nanomaterials to query the reservoir? Yeah. Maybe it'll happen. If you throw enough money at something, maybe it'll happen. But we've been down this road before. Like I said, in the early 80s, we tried microbial oil recovery. We even tried injecting oxygen into the reservoir to stimulate production. Do you know what happens when you inject oxygen into the reservoir? It's called a oxidation process, okay? Like rust? No. Like fire, okay? So that's what happened. Probably not real economic. Okay. Now let's move over to the next slide. And let's talk about the radial flow system. How many of you guys like my little radial flow picture here? So all flow is convergent into the well. And we're looking, this is the top, and this is the side. It's homogeneous. For whoever asked me that question, what does homogeneous mean? It means that the flow lines aren't doing this. They're actually just linear. Okay. And this is the governing equation. Again, it's Darcy's law. And now we're going to solve the radial flow equation for the pressure distribution in this. How many of you know that this is what we've been doing for the last 80 years in well testing? Who started this? Not me, thank you. Jerk. Anybody else? Muscat came after this. No, Archie was a petrophysicist. Sorry? Pekovich wasn't even a twinkle in his mom's eye by this time. Anybody else? I don't know who it was. Do you? It was the groundwater people. They were doing this in the early 1900s. They derived relationships for radial flow. This is supposedly, what's it called, Dylan? The Kelvin equation for heat flow. They were adapting it to fluid flow in porous media for the purpose of pump testing wells back in the teens and in the 20s. This is the so-called Tice solution whenever you go back and look at the transient. But in this case, we're only considering a geometry that's uniform, it's homogeneous, there's no compressibility, there's no accumulation in the system. So let's see what we're going to solve. Exactly the same setup. I sort of corrected the notes on the fly. There's a CX term here, and CR is equal to CX times 2 pi. Of course, the 2 pi came from here. Okay, no problem. Now we're going to integrate this. Marmina, what happens when you integrate 1 over x? But there's some steps in between. And if you were to not to show those steps, the punishment would be severe, right? Dilhan, explain it to him. Yeah. It's the difference between 100 or a 0, right? Okay. So this is PW and PR. So now we're going to integrate this. And what step did I leave out here, class? Oops, circled the wrong thing. The integral of 1 over x dx from 1 to x is equal to ln x, right? That's the definition. What are you looking at me like? Is this news to you? You didn't say all this other stuff. You didn't tell me the limits, which is sort of the story of your life. You don't know your limits, okay? All right, so we're going to integrate this. Instead of getting an x value, we get a logarithmic difference. The logarithm of r minus the logarithm of rw reduces to ln of r over rw. We then solve for rate. We do not have a pressure gradient in terms of x. We have a pressure gradient in terms of the logarithm of r. We solve this for pressure, at the wellbore, exactly the same as we did in the previous case. Natural log of R over RW. And when we plot it, we have pressure at any position, log R, going this way. For an A in this course, this is steady state. The connection between PE, or maybe PI, and PW. What does it look like before and after this? There's no way you would know unless you've taken the course before. What's it look like? Let's say I'm looking at a very small time. These are all parallel, by the way, even if I'm not drawing them very well. Okay? So as time propagates, T1, T2, T3, and then T instantaneous steady state. So the pressure is propagating out in the reservoir in this fashion. Did we do that with my little trick? Yes, we propagated like this. That's exactly what I'm suggesting here. Now, of course, all of you Pat Green fans or whoever the hell it is, the road goes on forever and the party never ends. Sorry? Is that the wrong guy? Oh, whatever. I knew it was an Aggie, so obviously he's not an Aggie. Everybody's got their cross to bear. Why am I drawing these lines as dashed? Come on, guys, focus. Why are they imaginary?
Because you're going past the extent of the reservoir.
Okay, who's talking? I can't see. Okay, explain that. In that case, pressure is greater than PI, right? So what has to happen? They got to turn. The maximum pressure is here. And that's what we're going to talk about. But as we pointed out, we cannot measure pressure in the reservoir. So what we're going to do instead is we're always going to reference the pressure at the wellbore and interpret the pressure behavior in the reservoir. You've never had a class like this before, have you? Where you're interpreting something. So that's what the first exam is going to be torturing you about the mathematics. The second exam is going to be torturing you about this interpretation thing. What's it going to look like after this? Again, why am I drawing dashed lines? Because there's a boundary here, right? And it cannot proceed past the boundary, just like it cannot proceed there. So what has to happen here is it has to flatten out. What is the pressure gradient at the boundary, class? dP dr at RE is equal to 0. What does this equation then say the rate is? 0. See how that works? What is this particular state known as? This is pseudo-steady state. This is transient. Dilhan, comment? This is no boundary. This is boundary. Okay? In this case, the propagation just continues to infinity. In this case, you have a fixed radius at RE. There's Petty 324 in a nutshell. And where do we measure pressure, class? At the wellbore. Where do we make our interpretations? Using wellbore pressure. How do we make these interpretations? We use models. Is there a possibility that you'll be wrong? Sure. Is a fractured well configuration going to look like this? Not exactly. What's not exactly mean? If the fracture doesn't work, then it could look like this. But if the reservoir is hydraulically fractured, it's not going to look like this, the profile. Okay. Now, Dilhan wants to go over this real quick. It's almost time to call it a day. Marmina, what's this called? The skin factor. This is for a cylinder. What does that mean, class? It means that this part of the donut is one permeability, and this part of the donut, well, actually, this is the whole, but there's two donuts, one on the outside, one on the inside. The one on the outside is chocolate. The one on the inside is glazed. Does that make sense? Okay. But what's the purpose of this discussion? You guys are starting to talk on me. Tell me what's going on. The PW star is the ideal pressure that this system should have. This is that equation we just derived. If the well is damaged, then the pressure will be lower than it's supposed to be. This is delta P skin. Okay? If the well is stimulated, the pressure will be higher than it's supposed to be. This is delta P skin. Okay? The reference is that it's P star minus something. So for damage, it is positive. For stimulation, it is negative. So when you hear a negative skin, that means the well's been stimulated. Okay? Now, how do we work around deriving the formulation for this particular case? Let me put it another way. For Monday, you might want to know how to do this. Is that a good way of putting it, Dylan? You might want to know of how to formulate a pressure distribution inside of a two-zone reservoir. Where is the solution to that found? In the notes. But we might be kind of sneaky, and we might change the problem a little bit. Is that right, Dilhan? Just a little bit. Not too much. So your exercise problem on Monday will involve the skin factor. Somebody tell me, for an A in this course, this is an easy question, the maximum damage is when the permeability in the skin zone, Ks, is equal to 0. What's the productivity of a well with Ks equal to 0? 0. What's the skin factor according to this particular equation? It's infinity. So there is no upper limit to how severely you can damage a well. Sort of, if you want to remember something, think about it that way. You can damage a well so severely it can never be repaired. On the other hand, what about stimulation? And we have to be careful because right now we're talking about cylinders. What's the maximum stimulation? Well, if the permeability of the inner zone is infinity, then the maximum stimulation is a fixed number. There is no infinite maximum right? What's the pressure drop across here? 0. That's the maximum I can achieve. Okay? When I'm saying that, I mean the pressure from here to here. That's the maximum I can achieve. Now this model is not exactly right for what happens in the field. Why? Why is this model not right for what happens in the field? Because things don't happen in a perfect cylindrical way. What kind of skin damage can we have? We can have skin damage due to perforations, skin damage due to slant wells, skin damage due to what else? Gas coming out of solution, partial penetration, fracturing, asphaltenes. What else? The list goes on and on and on. Let me ask you a very simple question, then I'll let you go. If you damage a well, can you guarantee that you can recover the initial productivity of that well? Are you absolutely sure? Good day.